This is Jude, Assistant Professor from Department of Physics, St.Joseph College of Arts and Science, Cuddalore. Now we can see the fundamentals in condensed matter physics. So we start from lattice points. Lattice is an ordered array of points describing arrangement of particles that forms the fundamental crystals. This is a fundamental. We can imagine this lattice point. In order to understand this, we can imagine the eggs in the tray. So each egg is considered as an atom, and where it placed is referred as a lattice points for understanding point of view. And this forms lattice points. If it is arranged in a systematic pattern, we can call it as a crystal. And the fundamental in this crystal is a unit cell. The unit cell is defined as the smallest block of geometrical figure repeating over and over in a space lattice in a three-dimensional pattern. So these lattice points in a three-dimensional pattern, when it is arranged in a systematic way, the fundamental unit, the smallest block of those repeated arrangements, we call it as a unit cell. And from the image we can say that there is a, in the right hand side there is a image where you can see the number of repeated patterns of lattice points, and the fundamental as a simple cubic is taken over here. So fundamental of these building blocks, we can call it as a unit cell, and those corners, 8 corners, we can call it as a lattice points where the atoms are stored. So what are coordinates of points? As we see in the image, the coordinates refers to x, y, z axis, and in x-axis it is A, and in y-axis it is B, and in z-axis it is C. Similar to that, the coordinates can be classified. It means it is represented in a crystallographic direction. The vector must passes through the origin. As you can see, the origin O, we can x, y, z axis can be drawn, and each coordinates is referred as A, B, and C. Planes, crystallographic planes, a plane must not pass through the origin. The intersections in terms of A, B, C, when we take the reciprocals, it is referred as HKL vectors. So what are Miller indices? It is a symbolic representation, vector representation, which gives the orientation of atomic plane in the crystal lattice, how the atoms are get oriented in that particular arrangement of atoms in the crystal, and we can refer or we can find it out by their orientation inside the crystals. And there are certain steps how to define these Miller indices, we can see. So the first one is primitive unit cell. What is the basic is primitive unit cell? When there is a repeated, and non-primitive, it is when it is not in the properly arranged manner, it is a non-primitive cell. And for finding the intercept, you can see the image below. There is a triangle which connects all the 3 intercept in the 3-dimensional axis: x-intercept, y-intercept, and z-intercept. So we can, if it is intercepts or equal, then the plane is said to be 1, 1, 1. These are the steps to follow to find the Miller indices, what is called as crystallographic planes. First one is the intercepts is for A, B, C. The intercepts can be taken as 1 by 2, 1, and 3 by 4. So you can see the intercept on A, which is in the x-axis. Though the intercept is in between the axis, that is exactly half of the in the plane, in the lattice plane. So it is 1 by 2, and you can see in the B, it is exactly intercept on the 1. There is a lattice exactly on the lattice point, and in C it is 3 by 4. And in the z-axis you can see the 3/4 is intercepted exactly on 3 by 4. So it is taken as 3 by 4. After finding these intercepts, we can take the reciprocals of it. It means 1 by 1 by 2, 1 by 1, and 1 by 3 by 4. Obviously we can get 2, 1, and 4 by 3. We have to reduce it by taking the LCM, so it is easy for us to reduce it to a whole number. There is 6, 3, and 4. Finding these things, the Miller indices is categorized as 6, 3, 4 for this particular plane. And next thing is Bravais lattice, and this is categorized as one dimensional, two dimensional, and three dimensional. And you said one dimensional, the position of vectors of all points or atoms in the lattice can be written in one dimensional and in two dimensional and three dimensional. So for in one dimensional A1, it is taken as B of x, A, B, and A or primitive lattices vectors. And in two dimensional we can see x, y, there are two axes, and A1 is taken as B x vector and A2 is taken as C y vector. And this the fundamental concepts of description of crystalline solids is that Bravais lattice. There is a fundamental description how it is atoms are placed. Bravais lattice is an infinite arrangement of atoms that looks like, as you see in that one dimensional, two dimensional, the distance between the interatomic distance in x-axis is taken as b and in y-axis taken as c in two-dimensional Bravais lattice. And this is the fundamental Bravais lattice in two-dimensional. The number of possible Bravais lattice of fundamentally in terms of symmetry, we can say in two-dimensional it is limited to as 5, and in three-dimensional it is 14. Variations are 14 in three-dimensional, and in two-dimensional it is 5. These are the basic 5 Bravais lattice in two-dimensional, and you can see here the A1 is not equal to A2. First one, general or oblique, the A1 is not equal to A2, and the angle is not also equal to 90 degrees. So these variations, these types of Bravais lattice is and the differentiation between these things are in terms of the angle and the A1 and A2 in two-dimensional. Since it is two-dimensional, it is A1 and A2. And the second one is rectangular. You can see it is exactly 90 degrees, but A1 is not equal to A2. The distance between the x and y axis, the atoms in the x and y axis is not equal. And the third one is center rectangular, and in these things it is the angle is 90 degrees, but x-axis is not look exactly in the y-axis. The distance in the interatomic distance is different. And in hexagonal, as you can see, it is not 90 degrees, it is 120 degrees, but A1 is exactly equal to A2. And last one is square, and all these things is angle is 90 degrees and A1 is exactly matched with the A2. The distance in x-axis is equal to the y-axis with respect to a particular crystal. And all these things are classified in two-dimensional Bravais lattice. And this is 14, in three-dimensional it is categorized in 14 dimensions. And you can clearly see over here what are these types. The classes are 7: cubic, tetragonal, orthorhombic, hexagonal, trigonal, monoclinic, and triclinic. All these, the P indicates the primitive and I indicates the body centered, F indicates face center, and you can see the number of arrangements over that. These are the main 7 crystal classes, fundamental classes, and there are 14 Bravais lattice with respect to it.